So now, we have two conductors there. So if we go to these two parallel plates, the question now is, what is now the capacitance then, according to our new definition of these parallel plates? Well, that capacitance C is the charge on one plate divided by the potential difference between the two plates. And the charge on one plate is sigma A. And the potential difference between the plates is the integral of E dot dl. They are separated there by a distance h. I will change that now to a d, because that's more commonly done, that the separation between plates is d. There was a reason why I didn't want to put a d there, because I didn't want to get you confused, but now there is no confusion. And so the potential difference is the electric field between the plates times the distance d. But E itself is sigma divided by epsilon 0, so we get here sigma divided by epsilon 0 divided by d. I lose my sigma, and so two parallel plates have this as the capacitance. It's linearly proportional with the area of the plates. That's intuitively pleasing. The larger the plate, the more charge you can put on there. And it's inversely proportional with the distance between the plates. The smaller you make the distance, the larger is the capacitance. Well, that goes back to this idea, that the closer A is to B, the larger effect that will have on the capacitance. And if you bring them very close together, this potential will go down, and so the capacitance will go up. So it's not too surprising that you see D here downstairs. The closer you bring the plates together, the higher the capacitance will be. Let us look at some numbers. Suppose I have a plate, very large, 25 meters long, and 5 centimeters wide, 25 meters long and 5 centimeters wide. I have two of them, called a plate capacitor. And let the distance between them, d, let the d be, let's make it very small, because we want a real big capacitor, 0.01 millimeters. Very small gap between them. So now I substitute the numbers in there. I can calculate the area. I have to calculate the area here for the plate in square meters, of course. Multiply by epsilon 0 and divided by d in meters. And when you do that, you find that the capacitance of this big monster is only 1 microfarad. It's not very much. And when you go to Radio Shack and you buy yourself a 1 microfarad capacitor, you don't buy something that is 25 meters long and yay big. Well, you may actually buy that without you realizing that. Because these large plates, these very long ribbons of conductors, two very close together, separated by some insulating material, very thin, they are rolled up often. And you don't notice that, but they are rolled up and they're put in a little canister, and that then gives you a parallel plate capacitor. I brought one with me. That's one that I have used for several years, but today I decided to cut it open for you so that you can look inside, and then you actually will see you're going to see it there. This is the canister in which it was, and so I cut the canister open, and when you look here, you see there is this conductor, looks like aluminum foil, and then there's insulating material, and then you find more conductors on the other side, and so it is rolled up. Here, if I unroll it here, I'm breaking it, but that's okay. So you see the idea of a parallel plate capacitor, how it can be rolled up nicely, and you're not realizing that you're really talking often about meters, many meters of material. Now, through chemical techniques, the distance d can easily be made 1,000 times smaller than this. And if the distance is 1,000 times smaller, then you would get a capacitance of 1,000 microfarad. Compare that with the Earth, which is only 700 microfarad. So a capacitor like this is 1,000 microfarad. If we bring the potential difference over here, then we get a tremendous amount of charge on here. In fact, if I hold this in my hands, And if I assume that the potential difference between my left hand and my right hand is 10 millivolts, then I would bring on this capacitor 10 microcoulomb. That is a tremendous amount of charge. In fact, 10 microcoulomb is the maximum charge we can ever put on the big Van de Graaff. We calculated that last time. If we put more on the Van de Graaff, it goes into discharge. And by simply holding this in my hands, I could put 10 microcoulomb here on this capacitor. Now you may say, well, yeah, but potential difference between your right hand and your left hand, 10 millivolts, isn't that funny? No, not really. In the future, I will give a lecture and then discuss electrocardiograms, and you will see then that there is a potential difference between the left side of your body and the right side, which is several millivolts. So it's not as artificial as you may think. Actually, we'll take a cardiogram in class so you can see it really working. How much energy can I store in a capacitor? Well, we already calculated that. We had the energy. This was the plate capacitor, 1/2 QV, and we can now substitute for we can substitute in there the capacitance C, and the C is Q divided by V, and so this is also 1/2 C V squared. That's one and the same thing. So either you take the charge on the capacitor multiplied by V, or you take the capacitance multiplied by V squared. The capacitance is never a function of the charge that is on the object. Here, if you look here, the capacitance is only a matter of geometry. And when you look there, the plate capacitor, it's only a matter of geometry. Never does the charge show up in there. So I mentioned that I can bring 10 microcoulomb on this capacitor, and yet on the Van de Graaff, I can also only bring 10 microcoulomb. That's the maximum I can do before it goes into breakdown. We can think of a capacitor as a device that can store electric energy. I will now return to my promise that I was going to demonstrate to you that I have to do positive work when I create electric fields. In other words, when I take these two charged plates and I bring them further away from each other, that I do positive work. And how am I going to show that to you? I have two parallel plates. They're on the table there. You're going to see them shortly projected there. And we have here a current meter. I put an A in there for amperes, symbolic for current meter. And I'm going to have a power supply and put a potential difference over here. This is the capacitance.